Good morning, everyone. Our project is going to be focusing on the large-scale production of photodegradable low-density polyethylene. These are the list of topics that we'll be covering today.
Hi, my name is Eman and I'm the Chief Marketing Officer of this project.
I'm Abdulrahman. I'm the Chief Technology Officer.
I'm Khaled. I'm the Chief Safety Officer.
I'm Faisal. I'm the Chief Operations Officer.
So plastic has been used all over the world due to its attractive features such as its high durability and its long life. But however, these features come into a cost that because plastic takes almost thousands of years to decompose, which causes a great harm to the environment in general. And in the Middle East, more specifically, are some of the largest plastic producers in the world. However, the recycling facility and the sustainable plastic there is very poor. So even though the recycling facility is very poor, there's a very high usage and waste generated in that region. That the waste generated is estimated to be equal to 2 million cars in weight, and it's the usage of plastic is 20 times the world average of the usage. To encounter these problems, some new plastic regulations has been put in place in that region. Saudi Arabia have made mandatory that all plastic be oxo-degradable by the end of September 2019. And another country in the region called Bahrain is preparing to charge for plastic bags and to make all plastics also oxo-degradable by the end of 2019. So what's photodegradation? Photodegradation is the process where the material, when exposed to sun rays for a long period of time, degrade. And we're focusing more on the polymer low-density polyethylene, which is widely available in the region given that it's petroleum-based, and also it's mainly used in single-use plastics. So the additive that we'll be looking at it will help initiate the photodegradation process and decrease the timeline for it to degrade. And we're looking into iron stearate, and based on literature, it says that it decreases the molecular weight of the polymer up to 90.2% in only 58 days, which could be very beneficial. So our mission basically is to decrease the negative impacts of plastic in the region and to help the waste buildup problem that's created in the region by using the sustainable solution that we propose, such as photodegradation, to help decrease the degradation time compared to traditional degradation methods that are used. So for our business structure, we're the Camel Consulting Group, and we're a startup initiative that was established in 2019, and we're going to be located in Kuwait, hopefully. And we help we help companies that already have plastic plants to create more sustainable plastic by suggesting sustainable solution in order for them to take their plastic producer and make it more of a sustainable plastic. So for our market analysis, we determined the ideal market to be the Middle East, given that we are from the Middle East and there is a huge problem going on with the plastic waste being built up and the conditions there. So we're hopefully going to partnership with large plastic companies that are in the 10 most plastic productions, such as SABIC and Kuwait. SABIC is based in Saudi, and it's one of the largest polyethylene producers in the world. And Kuwait is another company that's plastic company that's based in Kuwait, and it's another one of the top 10 plastic producers in the world. So our major competitors are Avani in UAE, which is which creates biodegradable plastic bag, and there is another company called GXT Green, which is based in Boston, Mass. But GXT Green, however, works with plant-based to create photodegradable plastic bag, while we'll be working with petroleum-based polymers. And we hope to make more research and development and propose more solutions to these companies. So our initial solutions for the material, we looked into bioplastic and modified conventional plastic. However, we ruled out bioplastic because of the lack of resources, and it's going to be very highly competitive to go into a market where conventional plastic have been used for a very long time. For our process, we looked into biodegradation versus photodegradation. However, we ruled out biodegradation because the location, the Middle East, is not going to satisfy the conditions since it's very hot, dry, and arid. And when it came to polymers, we looked into PPE, PET, and LDPE. However, we ruled out PPE and PET because they're usually used in packaging material for food and transporting food. And when it came to the additive, we looked into titanium dioxide, cobalt stearate, and iron stearate, but we choose iron stearate because titanium dioxide can be harmful to the environment, and cobalt stearate, as shown in literature, is not as effective as iron stearate is when it comes to photodegradation.
So to sum up, our final design solution is to produce photodegradable LDPE with iron stearate as the additive. So conventional plastic is used because it's readily found in the area, it's cheap, and it's easy to get into the market as opposed to bioplastic. Photodegradation was chosen because biodegradation can't occur at the rate that we expect it to because of the desert regions in the area. LDPE is the main component of grocery bags, and so single-use plastic is our main focus for the project. That's why we chose this specific polymer. And iron stearate, as Eman said, is environmentally friendly and also effective at degradation. And so to implement this solution, we decided on creating large-scale production of LDPE through the free radical polymerization phase. So this is the reaction in which we're going to produce the actual plastic, the LDPE. And so free radical polymerization is the process of creating polymers by radicals that are from an initiating molecule. In our case, we're going to be using benzoyl peroxide as the initiator. So in the initiation phase, the benzoyl peroxide breaks down into radicals and start attacking the monomer molecules. In the propagation phase, the monomers then attack other monomers, and that's how the chain grows. Finally, in the termination phase, radicals combine to produce stable chemical species, and that's when the reaction stops. And so these are the kinetic parameters used in our analysis. However, to create the actual large-scale LDPE production, there are several phases in the overall system. So there's a compression phase, reaction phase, separation, and finishing phases as well. This is our overall process flow diagram. So in the inlet, we have the ethylene that is sent to a series of compressors in the compression phase. It is compressed from a vapor to a liquid, a supercritical fluid, for the reaction. And before the reaction phase, the benzoyl peroxide is mixed in to start the reaction in the tubular reactor. After the products leave the reactor, they're separated in a high pressure and low pressure separator. Ethylene is recycled back according to the pressure. So for example, the ethylene coming out of the high pressure separator is already at high pressure, so it's sent to the high pressure compressor. The LDPE is at the bottoms and then sent to the finishing phase, in which it is extruded with the iron stearate and then dried into pellets. So this process occurs at high pressure at 2200 bar, high temperature with temperatures up to 300 Celsius, and can provide a conversion rate of 35%. And this is preferred over autoclave reactors, which only provide 22%. So after the LDPE has been produced with the iron stearate, we were able to investigate the mechanisms of photodegradation. So photodegradation, as Eman mentioned earlier, is a process in which plastic breaks down when exposed to UV rays. And so very similar to the first reaction that we mentioned, there's an initiation, propagation, and termination steps. In the initiation, oxygen and other impurities, such as our additive, absorb UV rays and turn into radicals. In the propagation phase, these radicals attack the polymer at different sites, and that's where the polymer breaks down. In the termination phase, the radicals combine, which results in several smaller fragments than the first polymer that we discussed. We were also able to perform a mass balance on the overall process according to literature and industry standards. And so we decided specifically to look at 400 kilotons of LDPE produced per year, which is the standard in the region. Specifically, SABIC produces this much LDPE per year.
Here is the overall piping and instrumentation diagram for the process. It shows the four phases that Abdulrahman mentioned earlier. The process begins with producing LDPE through the conventional method, then adding the additive iron stearate to the polymer to create photodegradable plastics. Moving on to the first phase of the process, which is the compression phase, which consists of the following major units. The tank is used to store and feed the system with the raw materials, and the heat exchanger is used to maintain the temperature of the system within a certain limitation. And the compressor is used to compress the ethylene coming from the suppliers in a vapor phase to a liquid phase. And the control systems that are used in this phase are the level on the initiator tank to avoid overflowing in the tank, and temperature on the heat exchanger to avoid overheating the system, and finally pressure on the ethylene tank to avoid building up pressure in the system. The second phase of the process is the reaction phase, which consists of the following major units. The reactor is used to polymerize the ethylene to polyethylene with the help of benzoyl peroxide that is being injected to the reactor in multiple stages. And the control system for this phase are the temperature on the heat exchanger and on the cooling jacket of the reactor in order to mitigate excessive heat and runaway reaction in the reactor. In addition to that, we do have multiple pressure relief valves that have been placed on the reactor in order to avoid building up pressure in the reactor, and that which may cause explosions. The third phase of the process is the separation phase, which consists of the following major units. The flash separator is used to separate the ethylene from the polyethylene and send it back to the compression phase. And the blower is used to provide the system with with sufficient air to push the polymers to the finishing phase. The control system that are used in this phase are a flow rate on the inlet stream of the inlet stream of the phase in order to regulate the inlet flow. Also, we have a pressure control system in the flash separators in order to maintain a proper pressure inside the separators. And finally, we do have a temperature control system in the two heat exchangers. The final phase of the process is the finishing phase, which consists of the following major units. The extruder is used to mix the polymers coming out of the separation phase and mixed with the additives coming from the silo. Then they end up in the dryer to dry out the pellets and be ready for shipping and packaging.
So using this information, we were able to construct an Aspen simulation for the project. However, it should be noted that Aspen does not have extruder or dryer blocks, and so the simulation only accounts for the first three phases, so the compression, reaction, and separation. So some stream results that we obtained from the simulation. The main purpose of the compressor is to compress the ethylene to liquid phase, and so the main change was increasing the pressure from 3 bar to 2200 bar. The temperature also increases as a result, and that's desired going into the reactor. For the reaction phase, the pressure remains constant. However, due to the exothermic reaction, the temperature increases to 270 Celsius. In the separating phase, we have the high pressure and low pressure separator. So the pressure decreases from 2200 bar back to 3 bar. The temperature also slightly cools, but we still need that temperature for the extruder. For each separation, we also have recycle streams, as mentioned earlier. And so for the high pressure separator recycle stream, the ethylene is sent back at 350 bar, but needs to be cooled down before it's sent to the compressor. And so the temperature is cooled from 270 Celsius to 60. Similarly, in the low pressure compressor, the pressure of the ethylene is at 3 bar, and the temperature is reduced to 25 Celsius. And these are the stream results summarized. We were also able to size the equipment according to Aspen and obtain the operating conditions. And so the separators occur from roughly 3 bar to 350 bar. The compressors range from 50 to 2200 bar, and the reactor also is operating at 2200 bar. For the temperature, the inlet for the reactor is at 125 Celsius, and the separators range from 240 to 270. The reactor was also sized to be 1,000 meters in length and are roughly 60 centimeters in diameter. So with Aspen, we were able to obtain significant useful information. So stream results was definitely one of the things we needed. We were also able to verify the production of LDPE according to the reactions specified. And so using this information, we started our initial safety and economic analyses. However, Aspen's not perfect, as I'm sure we all know. The mass balance of the simulation provided a 1-to-1 mass ratio of the initiator to the final product, which does not align with the chemistry. And that could be a result of the kinetic parameters used. However, any deviation from the set that we used resulted in errors. And as mentioned earlier, we were not able to model the finishing phase.
So, when it comes to safety, as you know, is one of the biggest factor in designing any chemical plant. So, as a firm, we're gonna make sure that our process adhere to the United Nations regulations safety in chemical plants, which is part of the International Labour Organization, as well as following the globally harmonized system of classification for labeling chemicals. In addition to that, the firm will make sure that its process follows the regulation at the region it operates at. In our case, the Gulf Petrochemical and Chemicals Association. Here is the safety data sheet for the material found in the system. As we know, the GHS system gives a signal word for each material, which shows how hazardous that material is. It's either danger or warning. Danger for immediate hazard, and warning for less hazardous. It also gives a pictogram for user-friendly explanation and demonstration. So for ethylene and benzoyl peroxide, they're both considered dangerous materials, so they need specific way of handling and storing. However, iron stearate is less harmful than the other two, and LDPE is not even considered as a hazardous material in the GHS system. Also, the biggest concern in any chemical plant is explosions and flammability. So, as you know, we run the reaction is a very highly exothermic reaction. It operates at high pressure and temperature. So we took the safety consideration of the reactor following a Chinese petrochemical model company. They used emergency pressure relief systems. They put 5 pressure relief valves along the reactor, as well as temperature transmitter sensor to sense any excessive temperature and send signal to the coolant jacket to mitigate that excessive temperature. We also took into consideration the inherently safer design, which consists of 4 major categories. Minimize, for example, in our case, we are minimizing the hazardous material, which are ethylene and benzoyl peroxide, as well. The second category is substitute, which means having safer equipment. So we are thinking of switching to safer mechanical pumps and pressure gauges, as well as using environmentally friendly additive like iron stearate. The third category is moderate, which means operating at safer conditions. So we thought of placing the control rooms away from the operation, also separate control rooms by units, so each equipment has its own control room, and finally simplify and make the process easier for operators to see and visually to follow. Also, we took hazard into consideration. We identified the problem that can occur in each equipment separately, then find solution for that problem and way to apply these solutions. In case of tanks, the main or major issue is overflowing, and that can be due to many causes like high inlet stream or valve malfunction. So in this case, we have the failed closed valve before the tank. Also, we have drain and flare. This is the main concern with the tank. The second concern is with the reactor, and as we mentioned earlier, the main concern is the high pressure and temperature, and that can be mitigated by having relief valves along the reactor, as well as temperature transmitter and alarm system. The third component is the compressor, and the main issue with compressor is that is the high pressure, and that can cause like burst in the pipe or the compressor itself, and this can mitigate by having regular maintenance to the system. Heat exchangers can have multiple of problems that can occur, and the best way to deal with this is to have regular maintenance. And also we have backup valves for to mitigate any problem that can occur in any specific heat exchanger. Separators can have also multiple problems like high pressure or high temperature, and that can be maintained by by having regular maintenance for the let down valve, which decreases the pressure of the inlet stream coming out of the separator or into the separator. Also, we have the couple other equipment in the system. We took that into consideration, and the best way to mitigate any problem is to prevent it at the first place. So we are thinking of having regular maintenance for all equipment all the time.
For the economic analysis, as a consulting firm, the economic evaluation can vary from a company to company based on the client requirements. For example, companies like SABIC, they already have an existing LDPE stream, so they only need the finishing phase of the process. While companies like Equate, they don't have the process for producing LDPE, so they need the whole technology from start to an end. Therefore, therefore the economic analysis have been conducted for the whole process based on the annual production rate of 400 kiloton of LDPE. The first component of the economic analysis is the capital cost, which accounts for the following parameters: ISPL, OSPL, and etc. These numbers were found based on the US Gulf Coast region. However, since we are operating in the Middle East, we used the correction factor, which is 1.7. That brings up the capital cost to $400 million. Here is the specifications for the capital cost. And the second component is the raw material cost. The cost of each raw material can be shown in the table, and the total raw material cost accumulates to $629 million, which is equivalent to 1,700 of LDPE per ton of LDPE produced. Here is another factor, which is the variable cost of production. The total variable cost of production was found to be $774 million per year, and the raw material plays a huge factor in it. Here is the specification for the variable cost of production. And here is another factor, which is the fixed cost of production. The total fixed cost of production turned out to be $15 million per year. And here is the specifications for it.
So we're expecting to selling our photodegradable product at the lowest price we can sell at, which is $2,150 per ton of LDPE. However, this price can vary based on our requirement needs. So our client needs. So for example, SABIC can sell it at different price, Equate can sell it at different price. However, we can sell it at $2,150. We are still way below the average minimum global price of conventional LDPE, which is $3,500. This turns out to have a net cash flow of $74 million. Also, here are some economic evaluation parameters we took into consideration. We took 15% interest rate, as well as the 5-year MSARS recovery plan for depreciation. Also, it's very important to mention that we are operating in Kuwait, which means there is no corporate tax over there in the Middle, in Kuwait specifically, and we are planning to have a 20 years planning horizon. So with that being said, after at year 12, we're going to break even for this process. And finally, the net profit, to summarize, the net profit of this project is $74 million, and the return of investment 19.7%.
So in conclusion, single-use plastic waste buildup has been causing great harm to the environment. So the production of photodegradable LPE could help decrease this buildup, and that could be done with adding iron stearate, as we mentioned previously, as iron stearate has been shown to decrease the average molecular weight of the polymer by 19.2% in only 58 days, according to literature. And the production of LDPE would be done through a high-pressure tubular reaction. And for the safety, we're taking into consideration material and equipment safety and the environmental consideration put in place. And the project seemed to be economically feasible and profitable with an annual net cash flow of 74 million per year. And for our future recommendation for the process, we hope to develop develop a more consistent control system and to do more chemical research on the process. And for the financial, we hope to retrieve more accurate data so we can use it while analyzing the finance and to estimate cost of each component. For our plant safety, we hope to have a disposable plan for the plastic waste buildup and also to have an emergency response plan and to have better training programs for the employees in the plant so we'd avoid any hazardous that could occur. So thank you. Any questions?
You guys were saying that you were having trouble with Aspen on the last part of your system.
Yeah, the finishing phase.
What were you using to model get estimates of the numbers you want out of production for your Aspen?
Sorry, could you repeat that?
If you weren't able to use Aspen to get some modeling or just to kind of see the rest of your process, what were you using to kind of get an estimate of that?
So the Aspen was mainly used to produce the LDPE. So starting from the raw materials to the final product. The main purpose of the finishing phase is just to mix it with the additive that makes it photodegradable. And so most of the stream results and the main safety hazards of the process occurs in the first three phases. So the compression, reaction, and separation phase. We hope to model the finishing phase in some other simulation, but Aspen does not have extruder blocks or dryer blocks, which is needed for that part of the analysis.
So when the plastics degrade, do they give off ethylene gas?
According to the reaction we have, no. So the photodegradation breaks down the plastic into smaller fragments, which makes it easier for it to naturally decompose. And so that the byproducts are, I guess, according to the bacteria used, that break down the plastic into other organic matter. Yes.
For your economics, you guys said you were going to break even in 11 years.
12 years
12
actually.
years. Is that normal for the industry? Or is that kind of a long wait time or short? Or?
It's more towards the late side, but as Khaled mentioned, we provided the minimum selling point to be profitable. And so different companies can charge different things. So for example, the US charges $8,000 per ton LDPE. India has $6,800 and we are only charging $2,000. So we use that as a baseline.
And that also can be different because some companies, they already have the LDPE process. So they don't need to add the whole thing. They're just going to add the finishing phase of the process. So it's going to be much cheaper and much profitable.
Yeah.
In terms of the plastic that you guys are going to produce, is there any issues with the structural integrity of the biodegradable plastic as compared to normal plastic? I know the Frito-Lay's company had used compostable plastic in their sunchip bags at one point, and they actually removed them from the shelves because of issues with integrity and because of noise. It's just going to be a problem. I was wondering if there's any sort of integrity issue.
Initially, we don't expect there to be any problem, especially since the additive is only at 0.5 weight percent of the total polymer. It's a very small amount that can do a lot in terms of degradation. All of the literature resources that we have focus more on the degradation time as opposed to the integrity. And so that's part of the chemical research that we plan on doing in the future.
Is there another questions?
Thank you.